welcome back. We are in Chapter 4, Section 5. This is the last section of Chapter 4, so we are almost done. And this one is about making connections. Back in Chapter 3, we learned about creating bootstrapped confidence intervals. This time in Chapter 4, we learned about performing randomization hypothesis tests. And you might have noticed that these two things have a lot in common. For example, in both of them, we're using a random process to simulate many, many samples, and then we're computing statistics based on those samples. And we're using what we find to distinguish between a typical value, which falls somewhere in the middle of a distribution, and an unusual value, which falls somewhere in the tail of a distribution. So in this section, we're going to formalize that, yes, there is a connection between these two. We're going to formalize what it is and how we use it. So the formal decision of a two-tailed hypothesis test is related to whether or not the null parameter falls within a confidence interval. So two things. When I say null parameter, I mean the number in my hypotheses. So say I have a set of hypotheses, mu is equal to 5 versus mu is not equal to 5. When I say null parameter, I mean the number 5. And secondly, the relationship is between a alpha percent significance level in a hypothesis test and a 1 minus alpha percent confidence level. So a hypothesis test with alpha set to 5% is equivalent to a confidence interval with 95% confidence. So that's the relationship. So 5% significance, 95% confidence. 1% significance, 99% confidence, and so on. In this example, we're going to stick with 95% confidence. So when the null parameter falls outside of a 95% confidence interval, we say that it is not a plausible value for the parameter to take, and we should reject the null at the 5% level of significance in a two-tailed hypothesis test. If, on the other hand, the null parameter fell inside the interval, then we'd say it is a plausible value. So we should fail to reject the null at the 5% level of significance in a two-tailed hypothesis test. And notice we're using this for two-tailed tests. Confidence intervals have two numbers in them, so we're dealing with the two-tailed test. We'll do an example now. In a Gallup poll of American adults in 2010, 59% of them said they favored a total ban on smoking in certain restaurants. In a similar survey a decade earlier, the proportion who favored the ban was only 40%. So we want to know, things are changing. So these two samples were used to construct a 95% confidence interval for the difference in proportion of support for a smoking ban in restaurants between these 2 years. The parameter we're estimating here is P2 minus P1, where P1 is the proportion of people who supported the ban in 2000, and P2 is the proportion of people who supported the ban in 2010. Remember, every time we use a symbol, we have to define it, and that is especially important whenever you have more than one symbol. And they found that a 95% confidence interval for this was 0.147 to 0.233. So does this confidence interval provide sufficient evidence at the 5% level of significance that the proportion of Americans supporting a ban on smoking in restaurants was different in 2010 than it was in 2000? Well, if the proportions were not different, what would happen to our parameter? Well, our parameter is P2 minus P1. If P2 and P1 weren't different, then our parameter would be 0. So if there was no change from 2000 to 2010, then we would expect to find 0 within our interval. But did we? No. Our interval started around 0.1 something, ended at 0.2 something. 0's not in there. So because the 95% confidence interval does not include 0, we do have sufficient evidence at the 5% level of significance, because this was a 95% confidence interval, to reject the null and conclude the proportion has changed. Okay, what conclusion, if any, could we draw at the 10% significance level based on what we just saw? What about the 1% significance level? Well, we were able to reject at the 5% level, which means we'd also be able to reject at the 10% level because 10% is going to be more lenient. We're going to go from a 95% confidence interval to a 90% confidence interval, and so we're turning down the confidence. This is fine. So we would again conclude that the proportion of Americans favoring the smoking ban changed over this decade. But what about for the 1% level? Well, we were able to reject at the 5% level, but that doesn't guarantee that we would be able to reject at the stricter 1% level, because now we're dealing with 1% significance, 99% confidence. The original statement that we had was not that strong, so here we cannot draw any conclusions. So this is just to show how we would make this connection between a confidence interval and a hypothesis test, and how we could extend this to other confidence levels, but we do need to be careful. So at this point, you might be thinking, if I can use a confidence interval to draw a conclusion in a hypothesis test, why do I even bother doing a hypothesis test? Finding a confidence interval was easier. What's the point? If we don't do a hypothesis test, we lose information about the strength of the evidence. So notice, we did know something about our significance level, but did we have a p-value anywhere? No, and that's something that we'd like. So that's why we do still do hypothesis tests. But it can be useful to us to know this relationship. And we had already practiced this and kind of hinted at it before back in Chapter 3, but now we've formalized it.